got to be careful. So for this, you can draw the cross section. This is the direction of Vy, which means the neutral axis is perpendicular to it. Here is point C, so the shear stress at the point C due to Vy is not 0. Because I can either look at the area above or below the point C to calculate that shear stress value. This becomes my A prime, and then I have the Y bar prime. R by 3 pi. So these are non-zero, so I can actually calculate it. What is the direction of the shear stress? The subscript on the second index is going to be x, because the area normal is x. The direction of the shear force is y, so this is tau yx. And so this is Vyq by IT. Vy is known to me. This was around 200 newtons. Please substitute the values. T suffix tau is 20, so all of this distance is T suffix tau. Mm. If I perform the substitution, this is what I'm going to end up getting. So Tc tau c due to Vy is going to be the following: 0.85 megapascals. Pointing vertically up, subscript Yx. It's pointing vertically up because the shear force is pointing vertically up. I have to do the calculations due to the shear force Vz. Okay? So let's take a look at that. C Vz, Vz, Q. If my shear force is Vz, the neutral axis is perpendicular to Vz, so this is going to be the y-axis, so I, y, y. This is ZZ, I'm sorry. It's sufficient to write it as IZ, but your book writes it as a double subscript, so it's following what it says. Theta. Draw the cross section. Don't need to keep drawing it every time, I'm just showing it to you here. Draw the direction of the shear force. Vz. This is the neutral axis for this particular shear force. Here was the neutral axis for the shear force Vy. The point C is on the neutral axis, so it is going to see the maximum shear stress due to the shear force Vz. You can do the calculations by either shading the area on the left or to the right of point C. I can take a look at this, call this as A prime, which is just half of the circumference, half of the total circular area. Then y bar prime is the distance from the neutral axis to the centroid of the shaded area. It's a circle. Does not matter whether you rotate a circle by 90 degrees or 180 degrees, this distance will remain the same for the semicircle. Okay, so this is still going to be the same as 4r by 3 pi. A prime is pi by 2 r square. Vz is known to me, 300 newtons. Substitute the numbers, which I'm not going to do today. It's 1.27 megapascals pointing to the right because Vz is pointing to the right. Okay, so this is 1.27 megapascals pointing to the right. Just take a brief pause. Subscripts. The second subscript does not change because the area normal is still the x-axis. So my second subscript is x. What's my first subscript? It is going to be the direction of the shear force itself. So this is the z direction. So this is zx. Just the nature of this does not tell me what the direction of the shear stress is. So it is important that I show it this way. Okay? Bending stresses. I'm going to start writing the normal stress due to the normal force right here. So sigma c due to nx. This is the same as we calculated before, so there is not much of a change. Subscript is xx. Nx by A, the area, 0.95 megapascals compressor. Same as that for point A. This was the same at any point on the cross section. So one value here, second one, third one, fourth one. You see, this simple, silly cross section has so many things going on. Then I have the fifth one and the sixth one, which is due to the bending moments mx and my and mz. Can you tell me, will there be any bending stresses at the point C due to the bending moment my? According to the bending moment my, the neutral axis is the y-axis, the point C is on the neutral axis for that bending moment, so there will be no bending stresses due to my. According to mz, the point C is on the neutral axis for this bending moment as well, so there is no contribution due to the bending stresses from mz. So that is easy for us, right? So point C on the neutral axis for both my and mz, which means that there will be no bending stress contribution from these moments. So sigma c my 0 with your permission, I want to get rid of this particular figure here. Everybody good with this figure, right? Okay, I'm going to get rid of it. I'm going to redraw it one more time, but just to show the stresses. Okay, it will be very cluttered if I just do it on the same one. So, this is the cross section. I have the point C. I'm going to draw a giant box around this point C. This is completely exaggerated. These are all supposed to be infinitesimally small. Okay. Then I will start drawing out the directions of the shear stresses. There are two shear stresses at the point C, both of them not in the same direction. There is one pointing up and then there is one pointing to the right. Okay, so first one. This is going to be tau c yx which is the same as that creature. Okay? Then I'm going to have one more to the right, which is tau c zx. Which is the same because there are no other stress contributions to shear stress at the point C besides this in that direction. This is the same as tau c dz zx. So this is the second shear stress. So one here, two there. Then do I have any other stresses at the point C? I'm going to have a normal stress due to the normal force which is pushing into this box. Right? So I'm going to have a normal stress, which is sigma c xx. This is the same as that. Sigma c xx. Then I have to draw the state of stress on a volume element, expand it out. For that, I'm going to get rid of this one here. Thank you. Is everybody good if I get rid of this? Okay. Bear with me for a few more minutes. Volume element. Axis system, Y and Z. Okay, so which means that my y-axis is pointing vertically up. This is my x, and that is my z-axis. On the face I see, I start off with one of the shear stresses. Okay, don't draw everything at once. Just draw one at once. Start off with the vertical one. I'm going to have one on the back face which is equal and opposite to it. I'm going to have one more on the top and one more on the bottom, which will create a couple moments to counteract the effects. Okay. Then I draw the other shear stress. You see there are two shear stresses which are in opposite orthogonal directions, right? So the other one is going to be pointing to the right, which means on the back face I'm going to have an equal and opposite one pointing to the right. It will start getting cluttered. Please keep everything separate. If you have drawn one, you can draw the rest of the three. Then I'm going to have one on the side face, and then one on the opposite back face. And then I have a normal stress pushing on both sides. So this is going to be tau C in the yx, and this creature is tau C zx, so that's my second shear stress. Then I have my sigma C xx on the back face, one more. And the very last step is to write the stress matrix. Start by writing the diagonal elements. There are no sigma C YY, sigma C ZZ, so those two are 0. So I'm just going to have one there, so that's 0.95 megapascals, and the rest of them are zeros. So this is in megapascals. The stress itself. Tau yx and tau xy are the same, so I can just directly fill it out as 0.85 megapascals. Tau xz and tau zx are the same, so I can fill it out as I had written it somewhere, but I think it's around 1.27 megapascals. Zero. Once again, very last one, okay? All the bending stresses or all the normal stresses on the diagonals. There's only one normal stress in the x direction, so the rest of them are 0. This guy is tau xy. This guy is tau xz. Tau xy and tau yx are usually the same symmetric, so if I write this out, I can fill this out. If I write this out, I can fill out the off-diagonal element symmetric with that. The rest of them are 0. Okay? We'll do one more problem on Friday and then I'll call it quits on this one. Okay? Thank you.
Nothing to do, it's like go back and like out of it.
Since the volume on it has.
I don't think I'm going to class.